Welcome back, Sarah. Let's dive into unsupervised learning. It's a different beast than supervised, right?
Exactly. No labeled data, just raw input. Imagine trying to sort photos on a social media platform.
You mean grouping similar faces without knowing who's who?
Exactly. And that's where unsupervised clustering comes in.
So, how do we know if our clustering algorithm is any good?
That's the tough part. No clear target. Visual inspection is often the only way.
So, how can we evaluate it properly?
Sometimes we can use external criteria, like the accuracy of the clustering against real-world data. But that's not always available.
Makes sense. So, these pre-processing steps, standard scaler, min-max scaler, are crucial, but how do they affect the results of our unsupervised learning?
They ensure the features have similar scales, which can be critical to the performance of algorithms like neural networks.
What about outliers? Robust scaler is a key player, right?
Right. It's more resilient to data points that are far off the mark. Imagine errors in measuring someone's height. They're outliers that we don't want to influence the results.
Interesting. How about something like topic extraction from text data?
It's like discovering hidden themes in a large corpus of documents. Finding patterns.
A great way to uncover hidden trends.
Exactly. Dimensionality reduction is another core concept here. Summarizing large datasets into something more manageable and insightful.
So, these techniques are about simplifying the data so other algorithms can then understand and perform well?
Absolutely. Making sense of a lot of complicated data.
So, for practical implementations, these are often a crucial pre-processing step?
Definitely. Unsupervised learning can often help unlock hidden patterns and make supervised learning more effective.
Great summary, Sarah. Thanks.
My pleasure.
So, Sarah, we've seen how scaling data affects algorithms. But, it seems like something tricky happened with that min-max scaler example.
Yes, Jane. It's important to be aware that the min-max scaler, like other scalars, applies the same transformation to both the training and test sets. This is absolutely vital.
Why is that important? Why can't we just use different scaling parameters for each?
Well, imagine training a model on a highly specific range, and then testing it on data outside that range. The model might not generalize well.
Makes sense. So, the training and test data are treated as the same dataset transformation-wise, even though they are different datasets in the end?
Precisely. The transformation is based entirely on the training data's characteristics. That same transformation is then applied to the unseen test set.
So, that's why we saw those values outside the 0 to 1 range in the test set? That's not supposed to happen. Why?
Because the min-max scalar scaling is based on the training set. Its min and max values are used. The test set data didn't inform the scaling.
Okay, I see. So, consistency is key. What if the min and max values in the test set are totally different from the training set?
Then the scaling on the test set might not be optimal, potentially underperforming the model. The model will be exposed to different ranges, and that can be problematic.
Ooh, interesting. Are there other scaling methods that might handle this better?
Yes, there are. For example, standard scaler, which centers data around 0 and scales to unit variance, or robust scaler, which is less sensitive to outliers.
So, different scalars have different ways of handling data. Important to consider that. What's the best approach, really?
There's no one-size-fits-all answer, Jane. The ideal choice depends on the specifics of the data and the algorithm used. Experimentation and consideration of potential issues are vital.
Great point. Thanks for clarifying, Sarah. Now I see how crucial it is for scaling consistency.
You're welcome, Jane. Always important to think about how transformations impact both the training and testing stages.
Sarah, that example about the different scaling methods, it's really clear now why consistent scaling is so crucial.
Absolutely. Imagine applying a completely different measuring stick to the training and test data.
Yeah, completely off. Makes total sense. So, fit_transform, a shortcut for scaling?
Exactly. A more efficient way to do fit than transform all at once. Sometimes you can really speed things up.
Cool. And the example shows how the SVC model performs much better after scaling.
Exactly. Scaling can dramatically improve a model's accuracy. The visual representation is really insightful too.
That's true. It makes a big difference in accuracy. So, how do we pick the right scaling approach?
It depends on the data's distribution. For example, standard scalar is good for data with normal or near normal distributions.
And are there other scalars?
Yes, robust scalar is great when you have outliers. It's less sensitive to those extreme values.
So, robust scalar is like a more resilient scalar?
Exactly, Jane. More robust to unusual data points, which is important in many datasets.
Interesting. So, are there any real-world examples where inconsistent scaling was a problem?
Sure. In finance, for instance, you might have certain stock prices that are exceptionally high or low.
A good point. If we scale those differently in training and testing, it would be a really bad outcome.
So, your model, while fitting with training data with some extreme stock prices, would not generalize to the test set which doesn't necessarily have those extreme prices.
Makes sense. So, should we always use fit_transform?
No, Jane.
It depends on the specific model and its performance needs. There is no magic bullet. Each situation demands different approaches.
Excellent. Clearer now than ever. So the takeaway is, scaling consistently is crucial, but choosing the right scalar is crucial too.
Exactly. You've got it. Always consider the potential for errors and limitations in your choices.
Thanks, Sarah. That was really helpful.
My pleasure, Jane.
Okay, Sarah, we've been talking about scaling data. Now, what if we have a dataset with tons of features, like the breast cancer dataset?
Exactly. That's where unsupervised learning methods become valuable for transforming data.
Interesting. Can you explain?
Let's say we want to visualize it. Imagine a 30-dimensional space. It's almost impossible to visualize.
Totally. So what do we do?
Dimensionality reduction techniques like PCA come in handy. PCA finds the most important directions in the data, the directions of maximum variance.
Like, what exactly does that mean?
It finds principal components. Think of them as new, combined features that capture the most information from the original ones.
So, we're condensing it?
Exactly. Instead of 30 features, we might condense it to just a few key components.
How does PCA work, exactly?
PCA subtracts the mean, then finds directions in which the data varies most. The first component is the direction of maximum variance, and subsequent components are orthogonal to previous ones.
So, it's like filtering the noise?
In a way, it emphasizes the most significant parts of the data.
And then we can visualize this reduced data?
Exactly. We can plot it in a 2D or 3D space to get a better visual feel for the data distribution.
That's cool.
It's also a way to reduce the computational burden.
Right.
So, we use PCA for more interpretable representations?
It's more than just interpreting data. We also use it for compression and other forms of feature extraction. PCA could reveal hidden patterns.
Very intriguing. Thanks for the insight.
My pleasure.
So, what are other methods? Any other approaches?
We have NMF and TSNE, each with its own application. NMF is great for feature extraction. TSNE for visualization.
Fascinating.
It's about finding the best representation for the job.
Thanks, Sarah. That's fantastic. So, Sarah, we've been looking at scaling. Now, imagine a data set with loads of features, like the breast cancer one. How do we even visualize it?
Yeah, it's overwhelming. Histograms give us a simpler way to look at the data distribution for each feature.
Interesting. What are histograms showing us?
They show how often each feature value appears for different classes, benign or malignant. This lets us see which features are more likely to differentiate the classes.
So, histograms alone aren't enough. What's next?
PCA comes in. It finds directions where the data varies the most.
So, it's like finding the main directions of spread in the data?
Right, and those are the principal components. We can reduce the data to just a few important components to visualize.
So, are we throwing information away?
Not really. We're finding the directions with the most variance.
Okay, but how do we pick the right number of components?
Well, that's a tricky part. It depends on the application and how much info you want to keep.
So, we're looking for the sweet spot, right?
Exactly.
How do we interpret those components, though?
They're combinations of the original features, not always easy to understand directly, but it's a powerful tool to highlight relationships between features and classes.
So, a 30-feature dataset gets condensed into 2 features for a scatter plot, and we still get useful insights?
Yeah, the malignant and benign classes often separate well in this lower dimensional space.
And that means?
A linear classifier might do a great job separating them.
So, it reveals the structure hidden in the raw data?
Absolutely.
Sarah, what are the limitations of PCA?
The axes are sometimes hard to interpret, since they combine multiple original features.
So, PCA isn't a magic bullet, right?
No, it's a tool with strengths and weaknesses.
Is there a scenario where something else might be better?
Absolutely, TSNE for visualization in some cases.
Great discussion, Sarah.
Thanks, Jane.
So, is PCA critical for further feature engineering?
It helps to highlight features and relationships, often a huge help for further analysis.
Thanks for explaining this so well. Sarah, you mentioned how the principal components are combinations of the original features. Can you elaborate on that?
Sure. They're like new axes in your data space, aligned along the directions where the data varies the most. Each component is a weighted sum of the original features.
So, these weights tell us something about how each original feature contributes to the new component?
Exactly. A high weight means a feature heavily influences that component. A heat map shows this clearly.
A heat map? Interesting.
Quickly, it visualizes the component loadings, the weights. The color intensity shows the magnitude and the sign.
So, in the breast cancer example, all features had the same sign in one component, meaning
they're generally correlated. If one feature increases, so do others. The second component had mixed signs, meaning
so it combines features in more complex ways.
Yeah, understanding these combinations is tricky, and why heat maps are helpful.
What's a real-world example?
Face recognition. We're using PCA to extract features from images. Imagine thousands of pixels. PCA gives us fewer but more important features, reducing the dimensionality while preserving important info.
But how do we know how many components to keep?
It depends. Sometimes we just need to visualize in a two-dimensional space. Other times, more components are necessary for better extraction.
What if there are a lot of images of George W. Bush, like in the face dataset?
That's a data skew, and we need to address that. We took only 50 images per person.
So scaling is important then?
Absolutely. It makes the PCA more robust. Without scaling, features with larger ranges could dominate the results.
How else can we deal with skewed datasets?
There are different sampling techniques.
So, Sarah, why are the visualizations important?
They help us understand the data. Histograms show distributions. PCA shows relationships between features in a clear way.
Do you see any limitations of using PCA in this scenario?
The new axes aren't easily understandable.
So it is not a perfect method?
No, it's a powerful tool with limitations. Sometimes other methods like TSNE might offer better visualization.
So, we're not just looking at the numbers, but also at the bigger picture?
Definitely. It's about understanding how the data is structured. The visual tools help us do that.
Thanks, Sarah. It's clear how PCA has significant applications in analyzing datasets.
Glad to help.
So, Sarah, you mentioned that raw pixel comparison isn't the best way for face recognition.
Why?
Well, imagine shifting a face just a pixel to the right. That's a big difference in pixel values, but it wouldn't change how we perceive the face.
So, the algorithms see differences humans don't.
Exactly. PCA helps us find a different way to represent the data.
And how does KNN fare using those new components?
Much better, actually. We got a 36% accuracy using the principal components instead of 27% with the raw data.
Wow, a significant improvement. How does whitening help here?
It rescales the components, so all have equal weight, preventing features with larger ranges from dominating.
How do we see these principal components?
They're visualized as images.
And what do these images show?
The first few capture basic patterns like contrast between face and background, or lighting differences.
So, those principal components don't directly represent a nose or eyes.
Right. They're mathematical combinations of pixels.
So, how good is this interpretation really?
It's a good start, but it's still not exactly how a human sees a face. We're looking at things like contrast and lighting, not the features themselves.
Is there a way to improve it to be more like how humans perceive faces?
Potentially. Adding other image processing or feature extraction techniques might help.
Maybe we're not looking at the right features.
Exactly. PCA is great, but it's about understanding its limitations in this case.
So, a better method for feature extraction might be necessary?
Certainly, other methods might lead to better results.
So, are there better classifiers than KNN?
Yes, there are definitely.
What about using, deep learning models?
Deep learning models are promising for images but require a lot of training data.
More data is probably needed if we want better recognition.
Right, you're absolutely right.
But we can already see that PCA helps significantly.
Yes, PCA is a really valuable technique here.
Great insights, Sarah.
Thanks, Jane. Always good to discuss these ideas.
Makes me want to dive deeper. So, Sarah, you mentioned how PCA can reconstruct faces. Can you elaborate?
Imagine building a face from its essential parts. More components mean more detail.
So, the components almost act like building blocks?
Precisely. And it's interesting how fewer components capture the general shape and orientation, while more recover finer features.
Interesting. And these scatter plots?
They show the data in a reduced space, focusing on the first two principal components.
But what if the classes aren't well separated in this space?
Means the first two components don't capture class distinctions effectively.
That makes sense. Now, NMF? How does that differ?
NMF finds non-negative components. Think of adding light sources to create a final image.
Like blending colors. Why is that useful?
More interpretable, especially for data where components are naturally positive.
Like image generation?
Potentially. It gives us different building blocks. Imagine we could use this for faces that are added up by lighting conditions.
Fascinating. So, which is better for face recognition? PCA or NMF?
It depends. If we need a more structured representation, where negative components might occur, PCA might be best. Otherwise, NMF's direct addition approach could be beneficial.
So, when might we choose NMF?
When the data is additive, like multiple light sources adding to a final image.
Okay, but how do these reconstruction errors translate to accuracy?
More error in reconstruction often means poorer classification.
So, we should look at both.
Absolutely. We can use both to explore the data.
What about computational time for both?
PCA is generally faster. NMF sometimes takes longer for complex models.
So, understanding the data's nature is key.
Absolutely. Understanding the source data, the way an image is formed, is helpful.
Great insights. This is fascinating.
It is.
Thanks, Sarah. Sarah, you said NMF components are non-negative and unordered. Can you explain that in a simpler way?
Imagine building a house. PCA uses both positive and negative materials like bricks and holes. NMF uses only positive materials like bricks.
Interesting. So, NMF's components have no inherent order?
Exactly. They're all equal, like workers on a construction site.
Does random initialization matter?
Yes, it can affect the specific bricks but not the overall house's shape in simple cases.
But reconstruction quality? Worse than PCA?
Slightly, it's not optimized for that. It's more about finding patterns.
So, NMF isn't about perfect copies?
No, it's about meaningful patterns like the angle of each brick, even if some are hard to see.
How about the face examples? NMF components, like what did they reveal?
Faces rotating right/left like different angles in an image.
That's cool. NMF picks out angles that PCA maybe misses.
Exactly. NMF excels at signals like audio or mixed signals.
Like separating sounds in a crowded room?
Right. Or finding genetic sources within a mixture.
This signal decomposition, is that the core concept?
Yes, finding the hidden parts of the mixture. NMF looks for positive building blocks.
Okay, and the synthetic example. How does that relate?
It shows how NMF finds the individual sources in a mixed signal, while PCA struggles.
But PCA is good at explaining the variation, right?
Yes, but NMF gives us structure. Which is better depends on our goal.
So, which is better for faces, PCA or NMF?
It depends on whether we need perfect copies or patterns like different angles.
Computationalkost?
PCA versus NMF?
PCA is quicker, but NMF can be slow for complicated models.
So, we need to consider our goals? Like looking for hidden stuff?
Absolutely. It's about the specific information we need.
Thanks, Sarah.
You're welcome.
Sarah, we've been looking at ways to simplify data. PCA, NMF, now what?
We're moving into more advanced visualization. Manifold learning. Think of it as creating a more nuanced map of the data.
PCA was like a basic map, right? Flat and might miss details.
Exactly. TSNE, a specific type of manifold learning, is like having a 3D map of data in 2 dimensions.
Wow, so we can see data in 2 dimensions without losing much?
It tries to preserve relationships between data points, making similar things closer.
So TSNE is more about relationships than just variance?
Precisely. See this handwritten digit example? PCA struggled to separate the different types.
But TSNE separated them.
Yes, and this is key to TSNE's amazing at visualizing clusters.
Wait, a precursor to clustering?
Maybe. It helps us visualize how data points group together.
So TSNE can make hidden patterns visible?
Potentially. Think of it like identifying hidden cities on a globe.
It's like a more powerful microscope?
Kind of. Zooming in on specific relationships, but it can't always give you exact copies of data.
So, can't use it for predicting?
No, it's not meant for prediction. It's all about seeing patterns.
So, what's the catch?
It's great for visualization but doesn't work on new data.
So, just for exploring data?
Mostly. It's excellent for exploratory data analysis, but not the best for making predictions.
Is there more to manifold learning?
Yes, many algorithms like TSNE, but each has its own strengths and weaknesses.
So, which should we use? TSNE or PCA?
Depends on the goal. PCA is simpler. Great for a first look. TSNE for seeing clusters more clearly.
Thanks, Sarah. Fascinating. Sarah, we've seen how TSNE can highlight patterns, like the different types of handwritten digits. Now, how do we group those similar digits together, rather than just spotting them?
That's clustering. Imagine sorting apples, oranges, and bananas.
We group similar fruits.
K-means is like a smart way to do that for data. It finds centers of groups and assigns points to the closest center.
So it finds cluster centers.
Exactly. It's like having a few key landmarks and every point gets assigned to the closest landmark.
So, we specify how many centers, how many groups.
Yeah, that's the K in K-means. 3 groups for the digits 2 or 5 depending on the task, and this changes the clusters found.
How does that work, exactly?
It starts by randomly placing centers, then assigns each point to the closest one. It then recalculates the center, and reassigns again until the assignments stop changing.
That sounds kinda like a dance.
Well, an iterative process. The algorithm does a dance.
And does the specific number of centers matter, Sarah?
Definitely. Too few and it might miss important patterns. Too many and you might get too granular. Finding the correct K is crucial for accurate representation.
Are there pitfalls, Sarah? Are there situations where K-means might give us the wrong picture?
Yes. K-means assumes all groups have similar sizes and shapes. If your data is in weird shapes, it may not work perfectly. Imagine trying to group irregularly shaped clouds in space.
So, it's not perfect.
Not for every type of data, but it's a good starting point.
And there's gotta be a better way if the groups aren't circular.
Right. There are other clustering methods.
Are there ways to tell if a clustering method is good? Like a quality check?
Yes, there are cluster evaluation metrics. Like looking at how points within a cluster are similar and different across clusters.
So we need to consider how to choose K and whether it's suitable for the data plus quality metrics.
And evaluating the method.
Fantastic. I think we need to delve into other clustering methods. Sarah, Those examples really highlight a weakness of k-means. It seems k-means struggles when the groups aren't perfectly round, right?
Exactly. Imagine trying to group people based on their height and weight. If some groups are more tightly clustered than others, k-means might not capture those nuances.
So, k-means isn't universal.
Nope, not for all datasets. Figure 327 shows how uneven densities can mess up the results.
It looks like it's trying to force round clusters onto data that just isn't round. Like really trying to fit a square peg in a round hole.
Precisely. Its assumptions about evenly sized spherical clusters fail when dealing with real-world data.
So, we have to watch out for those situations with k-means.
Definitely. And see how it performs before trusting its result.
The other figures showed k-means failing with stretched clusters. Figure 328. 2.
It's sensitive to the way the data is spread. If the clusters aren't roughly spherical, it struggles.
There are better methods for handling those types of situations. What's an example?
Yeah, other methods like DISCAN exist. They can handle more intricate, non-spherical shapes.
It seems like k-means isn't the best for all situations then.
It's a simple algorithm, but it's really important to know its limits.
So you're saying we should have a toolbox of different methods?
Absolutely, and know when to use which.
What about k-means as vector quantization?
It's not just for clustering. You can think of it as a way to approximate data using a limited set of vectors, the cluster centers.
Wow, it's not just for grouping stuff.
Think of it like a code book. Each data point gets a code, cluster center, and is represented by it.
Kind of like the way we use a limited palette to represent colors and images?
Absolutely. A lossy compression technique in essence.
K-means gives a quick result.
Often, but you need to be careful of the assumptions.
But when would we use it?
It's great for situations where the clusters are expected to be roughly spherical and similar in size.
Okay, so choosing the best tool for the job matters.
Absolutely. Knowing the data's structure and potential shapes helps choose the correct method.
That's super helpful. Thanks, Sarah.
My pleasure.
So, Sarah, you mentioned that k-means might not always be the best choice. What's another approach?
Yeah. Imagine trying to separate different flower varieties with overlapping features. K-means might struggle. Agglomerative clustering offers another way.
So, how does it work?
It starts with every data point as its own cluster, then gradually merges the closest ones until we get the desired number of clusters.
Like merging groups based on proximity?
Exactly. There are different ways to measure that closeness, or linkage.
Like different metrics?
Exactly. Ward's method, for instance, aims for clusters of similar sizes. Average linkage considers the average distance between all points in each cluster, and complete linkage uses the furthest distance between points.
Interesting. So, agglomerative clustering is like building a hierarchy. Does that affect how we choose the number of clusters?
It builds a kind of tree showing how the clusters merge. It gives you more context.
So, is agglomerative clustering better than k-means?
It depends on the data. K-means is faster for large datasets and can be suitable for spherical clusters. Agglomerative might be better with clusters that are not easily defined.
So, it's not a simple better or worse. It's about choosing the right tool.
Absolutely. It's about understanding the data you're working with.
And k-means, for its speed, is suitable for which types of data?
Roughly spherical clusters of similar sizes.
So, agglomerative clustering is more complex, but potentially more adaptable to the structure of the data.
It can handle data better with varied cluster shapes and densities.
Can you give me a quick example, Sarah?
Definitely. Imagine you have a two-moon dataset. K-means might struggle separating them, while agglomerative, due to its hierarchical approach, can better handle non-spherical clusters.
Makes sense. It's like using a specialized tool versus a general-purpose one.
Precisely.
Can more clusters in k-means be an advantage in a particular situation?
Yes, with complex shapes.
Does it make it more computationally expensive, though?
More clusters mean more computation. The right choice depends on the balance between complexity and speed.
Thanks, Sarah.
My pleasure.
So, Sarah, we saw how dendrograms visualize hierarchical clustering. What are their limitations?
They're great for 2D, but visualizing in higher dimensions is tricky.
Right.
So, moving on, what about DISCAN? What's the key idea behind this method?
It's density-based, finding clusters as dense areas separated by less dense regions.
Like finding groups of closely packed points?
Exactly. It finds core samples, points surrounded by many others within a certain radius.
And how do we define that radius?
That's the EPS parameter.
And what's min_samples for?
It tells us how many points need to be within EPS to be considered a core sample.
So, it's like a minimum density requirement?
Yup.
Interesting. How does DISCAN differ from k-means?
K-means assumes spherical clusters. DISCAN can handle more complex shapes.
Okay, so DISCAN doesn't need the number of clusters specified?
Exactly. It's more adaptive.
So, Sarah, which method is better in your opinion?
Depends on the data. K-means is faster but assumes spherical clusters.
And agglomerative?
Agglomerative is useful when the clusters are not well separated.
DISCAN's good for non-spherical, and it doesn't specify the number of clusters.
Precisely.
What about computational cost?
DISCAN can be slower than K-means and agglomerative.
So, it's a trade-off between speed and adaptability.
Definitely. It might be slower on large datasets.
Can you think of a real-world example?
Customer segmentation. Identify groups of customers with similar purchasing behavior.
So, DISCAN's powerful when you have unusual patterns.
That's it.
How do you choose EPS and min_samples parameters?
That's a bit of trial and error. It depends on the data.
It seems tricky to balance these parameters perfectly, right?
In customer segmentation, you look for different groups.
So, DISCAN is powerful, but not always the fastest.
True, but it handles non-spherical clusters and doesn't need predefined cluster count.
Good insight, Sarah. Thank you.
You're welcome.
Sarah, the visualizations really show how sensitive DISCAN is to those parameters, right?
Yeah, EPS and min_samples are key. They define the density you're looking for.
So, EPS is like a radius, and min_samples is a density threshold.
Got it.
Exactly. Too small an EPS and you'll get a lot of noise. Too large and everything's one cluster.
And min_samples?
It's the minimum points within EPS to be considered a core point.
So, smaller min_samples means more points become noise, and larger means fewer points.
Exactly. This trial and error, is crucial.
You can see that from figure 337, right? It really highlights that sensitivity.
Yes. The different values show different clusters forming or vanishing.
What about data scaling?
It really helps. Makes EPS more meaningful. Imagine features on different scales.
Makes sense. So for complex shapes like two moons, DISCAN shines, right?
Exactly. It can find those non-spherical clusters. K-means struggles.
How does this compare to k-means from a practical standpoint?
K-means is quicker but assumes spherical clusters, which is a major limitation.
DISCAN is a bit more involved then.
Yes, but that adaptability is powerful.
So, are there circumstances where it's worth the extra effort?
Absolutely. Customer segmentation, anomaly detection, and more.
What about large datasets, Sarah? Is DISCAN still practical?
It can be slower than other methods on huge datasets.
So, you're saying there's a trade-off between speed and capability.
Precisely.
Great insight, Sarah. Thanks for clarifying DISCAN.
You're welcome.
Sarah, now that we've explored different clustering algorithms, let's talk about how to assess their performance.
Right. Evaluating clusters is crucial. We need ways to compare k-means, agglomerative, and DISCAN.
So what are these metrics like ARI?
ARI and NMI tell us how well the algorithm matches a known true clustering.
So if we do know the real groups, then that's useful. But what if we don't?
Right. Then we use unsupervised methods like the silhouette score.
And what are the differences between these methods?
ARI and NMI give a numerical score. Close to 1 is great, near 0 is bad. Silhouette scores measure cluster compactness.
So, we look at how well the clusters stick together, essentially?
Exactly. But, accuracy scores are a no-go for clustering, right?
Why?
Because cluster labels are arbitrary. You can swap the labels and get the same clustering.
So, accuracy doesn't tell us what's going on beneath the surface.
Exactly. ARI and NMI focus on cluster relationships.
Okay, so unsupervised methods like Silhouette often lack a clear baseline for comparison without ground truth.
Yes, well, they measure how compact the clusters are.
So, what are the drawbacks of using Silhouette?
It doesn't always work well on complex shapes, especially those that aren't well defined.
So, in these scenarios, we need more nuanced approaches, like robustness testing.
Yes, we can test the algorithm's resilience to noise or changes in parameters.
So, knowing the strengths and weaknesses of each method is crucial for real-world applications.
Absolutely. It's all about knowing the context of the data you're dealing with.
Thanks, Sarah. Excellent discussion.
You're very welcome.
Sarah, we've been talking about DISCAN, and now let's see it in action with that face dataset.
Right, how did the algorithm perform?
Well, initially, everything got labeled as noise.
What was the parameter?
Min_samples equals 3. It needed a bigger EPS.
EPS controls the radius around points. Increasing it connects points that are close together. So a bigger EPS might reveal clusters.
Exactly. With a larger EPS, we got a single cluster and many noise points.
Noise interesting. What does it look like?
They're odd images. People drinking, wearing hats, unusual angles or crops.
That's interesting. It's actually identifying what's different and what's unusual, the outliers.
So, we need a balance. Not too much noise, but enough to actually find the structure?
Exactly. And what about when you tweaked EPS more?
We saw that with different EPS values, you got a single large cluster or even multiple smaller clusters.
Aha! That implies the face dataset, while seemingly simple, doesn't neatly separate into distinct categories.
So it's not just finding patterns but also detecting exceptions?
Precisely. DISCAN identifies outliers.
So, what's the takeaway here for data prep?
Well, pre-processing the images might make the data more homogeneous. Cropping or better image quality, or even different features than pixel values might be necessary.
So, DISCAN isn't always the magic bullet.
It's iterative. We'll adjust, evaluate, and potentially use different algorithms too to gain insights from the data.
Great insight, Sarah. So, how can we formalize this iterative approach to algorithm robustness?
We can test it with many parameter settings, perturb the data by adding noise, or using a range of EPS values and evaluating using metrics like ARI or NMI.
Thanks, Sarah. This gives a clearer picture of real-world application considerations.
Absolutely. It's more than just running the code. It's about understanding the dataset.
Okay, Sarah, so we've seen DISCAN's limitations. Now, what do k-means and agglomerative clustering offer?
Well, these algorithms directly aim for clusters of similar sizes, unlike DISCAN's variable approach.
So, what's the output like? Cluster sizes?
K-means yielded clusters with sizes ranging from 64 to 386, quite uniform.
What about agglomerative?
More uneven from 26 to 623, but still more uniform than DISCAN's results.
Interesting. How did you evaluate these?
We used ARI. It indicated a somewhat low similarity between the two.
Low similarity? What does that tell us, really?
Well, it's possible those clusterings are somewhat different. There's something to be said about clusters of differing sizes.
The visualizations are interesting, showing cluster centers. What are those cluster centers?
Average images from those clusters.
So, not an actual person from the data?
No, it's a composite picture. It helps us see patterns in the data, but it's not a single image from the dataset.
ARI is a general metric, right?
Yes, and might not always capture nuanced differences, though for our case, it did help in determining less similar clusters.
And what's the real significance, the takeaway from the average images of the cluster centers?
They reflect typical facial orientations, expressions, and even accessories like collars, not perfect matches.
Right, so which algorithm is best for this specific face dataset?
That depends. If we need clusters of relatively uniform size, k-means or agglomerative would likely be better choices than DISCAN.
So, it's not about a perfect fit, but identifying valuable patterns within constraints?
Exactly.
Final thoughts?
Remember, selecting the correct algorithm is critical. It's not one size fits all.
Good point. Thanks for the insights, Sarah. Okay, Sarah, so we've looked at k-means and agglomerative clustering. What's the overall takeaway from these last analyses?
Clustering algorithms aren't perfect fits. Agglomerative with its dendrogram gives a visual hierarchy of possible groupings. It's useful for seeing how similar different subsets are.
Interesting. So, how do you decide which clusters are worth examining? Looking at the dendrogram, are there particular distances or patterns that jump out?
Well, there's no magic formula. I look for branches that seem to group similar faces together. But I still might need to see the faces to verify the pattern.
So, it's kind of manual? Do you need to visually inspect the clusters?
Absolutely. The dendrogram is a guide. You still need to look at the faces. It helps to identify which clusters might be more homogeneous.
Makes sense. What's the benefit of picking out 40 clusters? Why not just 10?
More clusters sometimes reveal finer distinctions. We get much more detail in the 40 cluster representation. It's often important to explore different levels of granularity.
So, you're saying sometimes more isn't necessarily better?
But exploring various levels of clustering allows for a finer understanding of the data.
How would you use these techniques in a real-world example, like customer segmentation?
Imagine you're a company segmenting customers. With k-means, you might get groups based on spending habits. Agglomerative allows you to see how different purchase categories cluster.
It's not just about the math, it's about understanding the customer.
Exactly. You use the clustering as a starting point, then use your domain expertise to interpret the outcomes.
Great insight. So, should we always prefer complete automation when it comes to clustering?
No, definitely not. In many real-world cases, exploratory analysis, often with manual insights, is crucial. It's about asking insightful questions and finding patterns that might surprise you.
Sarah, you've really opened my eyes to the value of these tools for understanding data better.
Thanks, Jane. It's really a combination of both mathematical approaches and business understanding.
Great conversation, Sarah. Thank you. Sarah, so far we've explored these clustering methods, but how do we actually use them in practice?
Exactly. Scikit-learn is a fantastic tool. It standardizes the interface.
Can you explain this estimator concept?
It's a class that bundles algorithms. You make a model object.
Like a blueprint for an algorithm?
Exactly. It has methods. Fit, predict, transform.
So, fit learns from data.
Yes, fit takes the data, learns patterns, and creates the model.
Predict makes predictions?
Yep. And transform changes the data, something useful for clustering or pre-processing.
How would we choose between predict and transform?
Predict outputs labels or predictions. Transform changes the data's representation.
Wow, so practical.
It's a great way to manage different tasks within a standard framework.
Super important. What about evaluating a supervised model?
Score. Method lets you assess how well the model performs on new data.
Great.
So scikit-learn provides a solid structure for handling machine learning.
Yes, it's consistent for a lot of algorithms, very powerful.
What about using it on actual datasets?
Easy. Just load your data, create your model, and use the methods.
Can we use different data formats?
Yes. NumPy arrays, sparse matrices, many formats.
This seems quite versatile.
Yes, it's incredibly powerful.
What other tools are there in scikit-learn?
Beyond clustering, scikit-learn offers dimension reduction.
How does this help with analysis?
Simplifies the data for more efficient insights.
That's great, Sarah.
Thanks, Jane.
Listeners, scikit-learn is a powerful tool. We encourage you to explore the library and apply these concepts to your own projects.
Great ideas.
Want to delve into this more?
Absolutely.
Fantastic. Thank you, Sarah, for sharing your deep understanding.
My pleasure, Jane.
Thank you for listening. Be sure to subscribe for more data insights.
Bye for now.
Bye.